Today we're going to have a discussion on lightning protection. Specifically, we're going to go into lightning protection for substations using the rolling sphere method as explained in IEEE Standard 998. Now, Joseph here, he's an electrical engineer, but he's pretty new to lightning protection, I'd say, and so he's going to have some questions during this training that I think many of you might have. Now, today's training focuses on substations and focuses on the rolling sphere method, but as we know, lightning doesn't discriminate. The principles that you learn in this presentation are going to be applied to other industries, not just substations. But since we are in the substation industry, we're going to focus mostly on that today. So with that, let's get started. All right. So again, the agenda for today is to talk about IEEE Standard 998, to dig into the different methods of protection. We're going to compare and contrast them. We're not going to go too deep into all of the methods. We're going to focus mostly on the rolling sphere method. Then we'll get into rolling sphere basics, and talk about some of the different protection zone geometries. And then we'll get into failure rates and show some common errors that folks have while using the rolling sphere method. So, all right, so this is a quick illustration of the fixed angle method. Now, this is the simplest method that is in the IEEE 998 guide. And what it states is basically you can erect a shielding electrode. Now, what do I mean by shielding electrode? Shielding electrode means any object that you want to, or that it's safe to strike. So a mast or a shield wire or something that's grounded, that if it's struck, it's safe. In other words, not your equipment, right? Your expensive equipment, your bus, your breakers, those are things you don't want to get struck, right?
Right.
So those things, that's what we want to shield from. So to do that, with passive shielding electrodes, we put up shielding masts and shielding wires. Those are things that can safely get struck and divert that energy to ground, so that your equipment doesn't get struck, right? So that's what we have here. So this is a shielding electrode inside a substation, and you can see that it's grounded. And this shielding electrode provides a shielding protection of, according to the fixed angle method, of 30 degrees from its highest point. So 30 degrees in any direction. Anything that falls inside the 30-degree window is considered protected. Anything that falls outside the 30-degree window is considered unprotected or exposed. Now, there are some additional exceptions to this, as stated in 998. If you have two of these masts close to each other, you gain a little bit of bonus protection. So if you had another mast right here, instead of 30 degrees, it would be maybe 45 degrees. And there's more details in 998 if you wish to explore that further. And this stems from the old Franklin rods. Benjamin Franklin was devising lightning protection. He was noticing, a lot of fires caused by lightning, and how can we prevent this? And back then, he postulated that it was a 60-degree window of protection. And so, over time, we've realized, well, maybe it's a little bit more conservative than that, and we've dropped it down to 30 degrees. And this is a perfectly valid method for protecting your substation. In fact, this is used a lot today, and it's also used. Our partners in the transmission line design will also use the fixed angle method.
So anything within the triangle is protected. Is that correct?
That's right. Yeah. According to this method, anything that falls inside this 30-degree window is considered protected. Anything that's outside is considered not protected. So you can see, we're showing a two-dimensional picture here, but you would get a cone. Right, you like an upside down ice cream cone shape from this, and then another name for this method is called the cone method. And that's why.
Okay.
So it's pretty basic, right? That's the best part about this. It's very simple. It's easy to do the math. and it's easy to do the geometry, and it's very basic. It gives you a very quick analysis whether something's inside the protection zone, like this equipment is, or something is outside the protection zone, like this. Let's talk about some of the pros and cons of it, though, or rather the cons of it. So it's found to be inaccurate at extreme heights. And what I mean by this is the simplest way to protect your substation with this method, it may not be the most economical way, but the simplest way would be to erect a very, very tall mast right in the center, right? And then make sure everything is inside that 30-degree cone, right? However, this method fails at very very tall heights. I'll give you an example. The best example is something like the Empire State Building, right? The Empire State Building, if you imagine it's a grounded structure, it itself is a lightning mass, right? And it would provide this gigantic 30-degree cone of protection around New York, right? So I know you used to live in New York. I don't know if you lived inside the 30-degree cone of protection of the Empire State Building. But yet, we find that a lot of buildings, maybe such as your building, I don't know, but a lot of buildings inside its 30-degree cone of protection actually do get struck. They are subject to lightning strikes, and the reason for this is because, again, this 30-degree assumption, it's not perfect. It's not a perfect scenario, and this method fails when you have very tall heights. And we're gonna find out why in a little bit. We're gonna learn more about lightning protection and the way lightning strikes, and find out why this fails. Another issue here is that it's a very binary protection analysis. Right, and so this is what you asked me earlier, right? You said, hey, so is everything underneath the red line protected? And I said yes, and everything outside the red line is not protected, right? It's either protected or not protected. Right. And that's simple, and that's good that it's simple. Yeah. But the problem is it's not practical, as substation designers and, protection designers, that's not always practical. Sometimes you want to be able to say, some sort of failure rate. For example, is this little piece right here that falls just outside of this zone of protection really completely exposed, whereas this little piece is completely protected? Right. I mean, that's impractical to think, right? And we know in reality the nature of lightning, that's not true. In reality, things have levels of protection. You could say we want to protect against 99% of lightning strikes or 90% of lightning strikes or something of this nature. Not either 100% protected or 0% protected. That's not the way lightning really works. And so this method doesn't allow us to provide some sort of level of protection other than 0 or 100%. Sometimes it's not always economical to protect everything in your substation. What if this is the only little piece that's exposed? Do we need to put another mast just to cover that little piece because this is technically 0% protected? Again, fixed angle method doesn't allow us for that sort of analysis, that variance. Right. And these next two bullet points they stem from that, right? It's binary protection analysis, and it ignores varying stroke current magnitudes. So again, varying stroke current magnitudes, not every lightning strike is the same. Okay, we're going to find out in a little bit that lightning can vary, and as it does, the way it strikes varies, and this method doesn't account for that. There's also no practical failure rate analysis for the uncovered regions. Like I said, in this previous example, if this is the only part that's exposed, how many times is it going to fail? Is it economical to put another mast up? Well, we don't really have a way to calculate what that failure rate is going to be, and then so that we can compare against the economics of is it worth doing or not. Right. So, any questions about the fixed angle method before we move on? No, right? It's pretty simple, right? Yeah. Very straightforward, very simple, 30-degree cone. Yeah. And it's good. Like I said, it works. Our folks in transmission line use it. If you can think of picture a transmission line, picture like a transmission line parallel to the ground, right? You got your 3 phases of a transmission line, and a pretty standard transmission structure. And almost always, at least here in the southeast, where we have a lot of lightning, there's always two lines above it, two shield wires that are above it.
Right.
And those two shield wires are designed such that it creates that 30-degree cone, that 30-degree shield over the three phases of the transmission line.
Yeah.
So that's how we design transmission lines. It works great for transmission lines, and we'll continue to use it for that because of how simple it is.
Okay.
So, all right, let's continue. All right, so the next method that IEEE 998 describes is called the empirical method. Now, empirical, if you remember, empirical means basically based on observation, right? Like based on experiment.
Right.
So this is not based on any kind of theory. And in reality, same with the fixed angle method, right? Franklin said, hey, if based on my observations, it feels like these things provide 60-degree protection, and then like I said, over time we've narrowed it down to 30. So, and we're going to find out that's the way lightning is. We just, I'm not a lightning scientist, but even lightning scientists today, we just don't know enough about the way lightning works to predict things with 100% accuracy. Lightning is such an interesting thing. It's high amount of energy in a very short amount of time. So it's tough to observe. It's very dangerous, obviously, to observe. It's hard to replicate. So, so a lot of these things are empirical, but they do call this the empirical method. And I don't know about the history behind the empirical method, but from what I gathered from what I learned is that a couple of folks set up an experiment. I think they created this kind of atmosphere. Maybe I've heard something like fish tanks and glass atmospheres and things like that, and they tried to simulate lightning. They tried to create voltages and create sparks and charge differentials, and they tried to simulate lightning in this small controlled atmosphere.
Wow.
And then they tried to observe, okay, what things are protected if we put mass up, and what things are getting struck.
Right.
And then they simply scaled it up. And that's how we get these curves. The way this works, and there's several curves like this, but H is representing the height of your mast, right? You have a mast or a shield wire or whatever. There's another one for shield wire, another chart for shield wire.
Okay.
But H represents the height of your mast. D represents the height of your equipment.
Right.
Okay. And X represents the distance away your equipment is from your mast.
Okay.
Right. So then from these ratios, you can kind of see how far away you can safely place your equipment. Let's give you an example. Right. Let's say it's 100 feet. Let's say you got a 100-foot mast.
Okay.
And let's say your equipment is 50 feet. Right. Is half the height. Right. So D over H would then be 0.5, right?
Right.
So 0.5, knowing that my D over H is 0.5, if I go down here and I follow this line, okay, and let's say I want 0.1% exposure,
right.
I'll explain what that means in a minute, then my X over H ratio needs to be, 0.6, let's call this 0.65,
okay,
right? So X to H would be the distance away I can place that equipment. So if H is 100 feet and my X to H is 0.65, that means my X has to be 65 feet, right?
Right.
Am I doing that right? Excuse me, 6.5 feet. I apologize.
Right.
No. Wait. I'm sorry. 65 feet. Yeah, certainly. Yeah.
So.
Sorry, I was thinking 10-foot equipment height, but no. We're talking 100-foot mass. So my X to H would say, okay, 65 feet away, you can place equipment that is 50 feet tall from a mass that's 100 feet away. So you get the idea. So
that's 100 feet tall, right?
Correct. 100 feet tall. What did I say?
You said 100 feet away.
My bad. Yes, 100 feet away.
65 feet away, I think.
65 feet away. So, okay, sorry, juggling a lot of numbers in my head here. So let's just go over that again to make sure we got it. So again, if you have a 100-foot mast, H is 100 feet, and let's say D is 50 feet, then your D to H ratio is 0.5. right? If your D to H ratio is 0.5, that means your X to H ratio needs to be 0.65. That means X has to be 65% or less of H. So again, if H is 100 feet, then X, the distance away, has to be 65 feet or less to maintain 0.1% exposure.
Right.
Okay, so this is neat. So what is 0.1% exposure? That means 0.1% of the time you're going to be subject to a lightning strike. So 0.1% of lightning strikes that are in this area are going to hit your equipment, whereas the other 99.9% will strike the mast instead.
Okay.
Now, if we're willing to accept a 1% exposure rate instead of 0.1% exposure rate, then we can put it further away, right? So to get to maintain the 0.5, you can see now we can put it 0.8 or 80 plus feet away, and we'll still get protection, but it'll be reduced protection, 99% protection instead of 99.9% protection. So,
and they found that this method works pretty well all the time.
Yeah, well, it does. It does follow these curves. There are utilities that use this very successfully. I've worked with utilities that have this written into their standard, and yeah, it works. It's very simple, right? It's easy to do the math, right? Even though I know we struggled with it a little bit there with the decimal point, but it's very easy math to do, and this chart provides everything for you. But there are some shortcomings, and let's talk briefly about what some of those shortcomings are. Remember we said that the fixed angle method has binary protection analysis. Everything's either protected or not protected, right? This gave us some better options, right? It gave us a 1% or a 0.1%, as opposed to either 100% protected or 0% protected, right? It gave us 99% protected and 99.9% protected. But you're still limited to those, okay? So it's a little bit better than binary. We're getting a couple more options, 1% and 0.1%, but we're limited to those. According to IEEE, I mean, this is the curves that they have available. There's a handful more charts like this, handful more pictures for different configurations, but there's still a limit to those configurations. So if you were to go through IEEE 998, if you were to look at that, there's a handful of these charts. Some show masts, some will show shield wires, some will show three-phase cable going into the page or three-phase bus.
Right.
But again, you're limited to those configurations. Well, what if your substation is built a different way and one of these configurations doesn't apply to you? Then you have to break it up, right? Then you have to say, well, this is similar to this configuration or whatever.
Right.
Another thing, another shortcoming of this method is that, well, what if these ratios don't apply to you? What if you were curious, if you go further? What if your equipment height is really short and you have the ability to go further? Can you? I mean, is it safe to just extrapolate this line further? The IEEE 998 advises you not to. It says it's not, because these are all experimental, numbers anyway, plotted. Now, some mathematician could come in here and figure out what the equation of this line is, right, and continue and draw the line out. But, without real data available, IEEE says, don't extrapolate this line beyond these ratios. And again, that means, what if you have equipment that's, if your mast is 100 feet and you have equipment that's further than 100 feet away, you can't use this chart. You're limited to that. So so that's another limitation of this. And then, what if you have some equipment that is like, just ends up right here, just a little tall, and ends up, outside your exposure? Again, just like we had with the fixed angle method, right? We talked about that piece that's a little bit outside of the cone of protection. Is it necessarily unprotected? I mean, is it worth protecting it? Do we need to go back and add a lightning mast? There's no way to analyze that. There's no way to say, well, Well, how often is it going to fail?
It's not very flexible.
Right.
Yeah.
It's not flexible. It doesn't allow you to say, well, this is a really cheap, area. This is an area that we can survive an outage, and yet it would be very expensive to put another mast in there, so it's not worth doing. Well, I mean, you could look at it and say, you could say those things, but you have no way to compare against it and say, here's how many times it'll fail, and what does it cost to protect it? Is it worth it? There's no way to do that analysis. So those are kind of the shortcomings of that. Again, a very good method, very simple and straightforward, but does have some shortcomings. Any questions about the empirical method?
No, it's pretty
straightforward.
Pretty straightforward, yeah.
Yeah. All right, so those are the other two methods covered in 998. But now I want to talk a little bit about what we came here to talk about, which is the rolling sphere method. Now, this is the most popular method. Again, other utilities use fixed angle and the empirical method, but by far most utilities have switched over to the rolling sphere method.
Okay.
This seems to be the most popular method. Here's just some brief history on it, which we won't get too deep into. But you may also hear it called the EGM method, the Electrogeometrical method. It's based on geometry of a rolling sphere, and so the EGM method describes how how lightning forms, and the rolling sphere method is another term that applies the EGM, the electrogeometrical model. Right. So this is the rolling sphere method is a way to practically apply the EGM.
Okay.
For vocabulary. So, all right. So let's get into what the EGM is. In order to do so, we want to understand lightning strikes. Again, I'm not a lightning scientist, and I don't claim to be. There's a lot of things about lightning that even lightning scientists don't understand. It's highly probabilistic. So I want to preface that's very important, because as we do these calculations, all the formulas that you see, yes, they're empirical, they're based on observation, and the protection zones that you see, we could claim that something is protected and then it receive a strike. Right. Again, lightning is highly probabilistic. We can't be 100% sure how it's going to behave, but based on the information that we do have with this method, we can feel comfortable that this is safe. It's not going to work 100% of the time. Even if you read in IEEE 998, it says there is no foolproof 100% way of protecting something against lightning, short of creating a Faraday cage, short of enclosing it in a grounded metal object. So, so keep that in mind as we go through these formulas. We're not going to spend a lot of time digging into the formulas. We're going to show you what they are and express some relationships, but we can dig into the formulas deeper or on your own at another time.
Right.
So,
okay.
All right. With that, let's get started on lightning strikes. So generally speaking, lightning, the reason for lightning is because you have a charged thundercloud, right? You've got a thundercloud that has this separation of charge. In this example, you've got a lot of minus charges on this side, and maybe some plus here towards the center. Mm-hmm. And again, that's not always the case, but for the most part. And this cloud wants to neutralize itself. So all these negative charges want to neutralize itself. And yes, it can, neutralize itself with the positive charges within its cloud. And you'll see that. You'll see, it's difficult to see for us from the ground, but lightning does strike, one cloud will strike itself. And you'll see lightning bolts jumping within a cloud.
The cloud just kind of lights up?
Yeah. I mean, you'll see that inside the cloud, you won't see the bolt to ground,
right?
Right. Or you'll see cloud to cloud strikes. That happens a lot, right? You'll see one cloud ionizing another cloud next to it that has the opposite charge, and they're both trying to neutralize. Again, this is the electricity is just trying to neutralize. But for the most part, lightning that we care about, lightning that's hitting the ground, lightning that's striking our equipment, how does it behave? So what happens is these charges, they build up these charges, this charge difference, and then the air around the cloud begins to ionize, right? It's searching for a path to neutralize the cloud. And so it zaps the air around it, right? It forms these little step leaders. Okay, they kind of form out in random fashion. You see, typically zigzag. I mean, it depends on the air around it, right? I mean, electricity is still going to take the path of least resistance, but it depends on the charges and pressures of the air and things like that. Several variables, but it's going to ionize around it, and it's going to kind of form in, for the most part, in random fashion. And then as the step leaders, they get closer to the ground. The ground has a lot of charge, right? Be that from, some folks I've heard say that it's from the sun and hydrogen atoms hitting the atmosphere and things like that. You get a lot of positive charges on the ground or what have you. But the ground itself think of it as just a well of charges, right? Yeah. And so it's a great source of charge for a cloud to neutralize. Right. So anyway, so the air, it's going to ionize the air around it. It's going to kind of go in random fashion. Eventually, it's going to get really close to some equipment or really close to the ground. Right. Eventually, it's going to do that. And when it does, right, now you've formed a path to the ground. You've formed a path to reach that well of charges. And as soon as you do, then you're going to see a bright bolt, right, that will go up to the cloud and neutralize the cloud. So you see that's the return stroke. I don't know, whenever maybe you were growing up, maybe you had a teacher or a parent or somebody tell you that lightning strikes up. Have you ever heard that?
I don't think I have ever heard that.
Yeah, okay. Well, I've heard that. I don't remember if that was Mr. Rogers or something of that nature, but the
I
reason
it struck down.
Okay.
That's interesting to me.
Well, and again, in some cases, it's based on current flow and which is current flowing up or down. Generally speaking, most lightning strikes form because of a negative charge on the cloud, but it can be the opposite. It can be a positive charge on the cloud looking for negative. Okay. And so it's when we talk about up or down, we're talking about current flow. But generally speaking, lightning does that return stroke is current going from the ground back up into the cloud. So your positive charge is going back up into the cloud. Right. So that's how that bright bolt is formed, and that is the muscle of the lightning stroke. That's the bright flash that you see, and that is the heavy current that's very dangerous, and it occurs over a very short amount of time. Okay. So this is great. This is, it's been very difficult to observe lightning. This gentleman, Tom Warner, had this high definition, I should say high refresh rate camera, right? And he was able to slow down, ultra slow motion, and was able to film this lightning strike. And so you can see what happens here, right? As this video resets, you see the step leaders forming. Yeah. And you see they kind of form in random fashion, and they're searching for that well of charge to neutralize the cloud. Right. And so they're just going in random fashion. It's important to note some of them are going back up, some of them are going sideways, a lot of them are going down, right? So and you can see somewhere here, here it is, right here. This is the step leader that touches ground first. Right? Ground or a tree or maybe a piece of equipment or whatever it is. But let's assume it's the ground, right? This is the one that touches ground first. And as it does, then once that step leader is within striking distance of the ground, then you see the bright bolt go back up, and it goes back up the same path that step leader formed, right? That zigzag path that came down, it goes right back up along exact same path.
Wow, that's amazing. Yeah.
So you can follow the path of current back up to the cloud to neutralize the cloud. So again, the ability to take this kind of video is relatively recent. The technology for this, but it proves the point of the step leaders forming in random fashion, kind of zigzagging everywhere, and then the bright bolt of it going back up the path of those step leaders. Right. Yeah. So, any questions about this or step leader formation or anything like that?
No.
Okay. All right. Great. Let's carry on. again, we said that the return stroke is what that bright bolt is. That's the dangerous amount of current. That's the high current is in that return stroke back up to the cloud, and that's what the bright bolt is.
Right.
That amount of stroke current, right? We're going to call that stroke current from here on out. That stroke current is a factor of strike distance. Okay, so what is strike distance? Strike distance is that last step leader to the grounded object. Okay, so that step leader is forming in zigzag patterns and neutralizing air around it, and then that last jump that it has to do before it hits a grounded object or something is the strike distance. Right. And that strike distance is, again, it's a factor of stroke current, which this makes sense, right? If you think about it, the amount of current I'm trying to dissipate as a cloud or whatever, or the amount of current I need from the ground to neutralize, if I have more current, if I need more current, that step leader is probably willing to jump farther, right? So it's going to have a longer reach. Right. So that last step leader, before it has to ionize more air around it, is willing to reach farther.
Just to make sure I'm clear about what the step leader exactly is, it's the very tip of one of those branches?
Well, we consider all these branches to be step leaders, right? So we would say this is a step leader, and then this is a step leader, and then this is a step leader, right? And so the last step leader is the one right before it strikes something, right? Now things that it wants to strike, grounded objects or the ground itself, are within reach. Yeah. So once those are in reach,
I thought that's what it was. I just wanted to make sure it wasn't the distance from the cloud all the way down to the thing, but it's just the very last little from that last elbow to the.
There you go. Yeah. Gotcha. Yep. All right. So no, that's a good question, and that step leader distance, which I'm going to refer to the reach of that step leader. Okay. You'll see why in a little bit, but that is how far that step leader can reach, is a factor of stroke current. Right. So, and here's the formula given by IEEE. Okay, there's a constant here. IS is stroke current, and then then S is the strike distance. So you can see if you have higher stroke current, you have a longer strike distance. Right. So now S, this strike distance, is going to be the radius of our rolling sphere. Now, we haven't got into exactly what the rolling sphere is yet, but just keep that in mind. S is the distance of your rolling sphere. Right. And so the center of your sphere is that last step leader, the origin of that last step leader. Right. Okay. So we'll get more into that. But so why a sphere? Okay. Again, last step leader, the origin of the last step leader, right? There's step leaders all the way down, and then another step leader stopped here, and now it's here, and now things are within striking distance of it, right? It's ready to strike something. Right. So this strike distance, which is a factor of the stroke current that it's trying to dissipate, this strike distance is this blue circle, represented by this blue circle. Right. So you can see here that it can reach this grounded electrode. Right. This is a dead end structure or a lightning mast or whatever it is. Right. It can reach. It's within reach of a grounded electrode. It is also within reach of a lot of this equipment. However, the thought behind this, again, this is not 100%, but observation tells us, for the most part, for the vast majority of time, if a step leader has a choice between striking your bus or striking a grounded electrode, it's going to want to strike the grounded electrode. That tends to be the path of least resistance. Right. All right. Why is that? Well, a number of different reasons why. Some say, well, it's higher, it's grounded better, things like that. Another key point is that this bus, is separated from ground with this insulator, right? So this is not a grounded object. Right. So to get to ground, not only does it have to traverse all this air and all the resistance up to here, it also has to get over the resistance of this insulator.
Right.
Whereas here, it doesn't have to get over that resistance, right? So if given the choice, it's most probably going to strike this.
Yeah.
Right.
Makes sense.
Yeah. Now, it could strike a grounded object here, like this object is grounded, right? But if it strikes that, if it strikes that without causing flashover to our insulators, then there's no damage done there.
Right.
So that's okay. But most probably, vast majority of the time, now I don't want to give a percent, I don't want to assign 90, 95, 99%, whatever it is. Again, lightning is a highly probabilistic phenomena, and we don't know exactly what it's going to do every time, but experience and observation tells us that if given the choice, it's going to strike the grounded electrode. Okay, so any questions about that?
No.
Okay, so let's look at another example, right? Here's another step leader. And the step leader, the origination point of this last step leader is somewhere here. Okay. Now, if you'll notice, this step leader can't reach this grounded electrode.
Right.
Right? Rather, it can reach all your equipment.
Right.
Right? Now, that means all this equipment is subject to a lightning strike. We don't know if it's going to get struck. Again, we don't know if it's going to strike some grounded part or the equipment. But it's not a grounded electrode. It's not a shield wire or a mast, which we again said is most attractive to it.
Right.
So, that being said, this step leader is dangerous. Right? It can strike something, and we can't divert it. We can't tell it to strike our grounded electrode instead.
Okay.
All right, so bad will most probably strike the equipment, and so these are the kind of strikes we want to avoid. Any questions about this?
No.
All right. So the strategy of the rolling sphere method, the whole idea behind it is to create a sphere with the radius equal to the strike distance that was associated with IS. Okay, we'll talk about how to get IS in a little bit, but we create a sphere. And then we roll that sphere through the substation. We go up and down, and then every time we hit a shielding electrode, every time we hit something that's safe to strike, we go up and over it. And the reason we go up and over it is because the surface of the sphere represents all the items that are within reach of that step leader. Right? The center of the sphere, if the center of the sphere represents the step leader, then the surface of the sphere represents all the items within reach, or the limits of the reach limit of that step leader.
Right.
Does that make sense?
Yes.
Okay. So if it can reach a grounded electrode or a shield wire, then there's no need to roll through it because we know it can reach it, so we'll move on. So that's why we roll.
You're going to tell us how to get the length of the step leader?
Yes. Yeah, that's to get that is going to be associated with our stroke current. Now, you'll ask me in a little bit what our stroke current is, and we'll get to that.
Okay.
But that's the strategy behind the rolling sphere. All right, and equipment that remains below the surface of the sphere is protected. So let me show you.
That'll make sense.
Yeah, so in this example, we have a sphere that we've defined, and we're rolling it from the left. Now, it's okay to strike the ground, so we rolled it on the ground. Okay. We're rolling it in from the left of this picture, and we hit this mast. When we hit this mast, we go, again, this mast is safe to strike. We want it to strike. So we're going to go up and over the mast, okay? And items that fall inside this area, under the sphere, is considered protected.
Okay.
Items that fall outside this area, or within the circle, within the sphere, are considered to be exposed.
Okay.
Right? This, for example, this piece of bus, let's say you have a step leader forming at this red X. Let's assume this red X is the center of this circle, right?
Right.
This is a step leader forming. This surface, this circle represents the strike distance.
Right.
The items that are within reach of a step leader forming here. And so you can see this mast is just out of reach of a step leader forming here.
Yes.
But this is not out of reach. This is in reach.
Yes.
So, given that this is in reach and this is not in reach, it's going to strike this.
Right.
Right. Presumably, it's going to strike this. So this is considered exposed to a step leader that forms exactly here.
Right.
That has exactly the magnitude associated with this sphere.
Right.
Okay.
You know, it's kind of reminding me of the. I was thinking, I can't remember what it's called, the tent pole method. The first one you mentioned.
Oh yeah.
It goes, angular, but now.
Right, the fixed angle method.
Yeah.
That's right. And you can see why the fixed angle method was so good for so many years and still is good.
Yeah.
Right? According to this method, this looks very much like a nice 30-degree fixed angle.
Yeah.
Right?
Yeah.
But and we'll get into some of the other shortcomings. However, if you raise this mast, right? Let's say we made it ridiculously tall.
Yeah.
If we made it ridiculously tall, this sphere doesn't necessarily. We still have the same kind of level of protection here.
Right.
Right. We'll get into that in a little bit, but that's a very good observation. But that was one of the failures we talked about.
That's interesting.
About the fixed angle method.
Yeah.
And why it doesn't work for really tall heights. Whereas this is a better method for really tall equipment. The fixed angle method is great and is still used for protecting buildings, for protecting, things that have where your mast heights are, 2 feet, 3 feet, things like that.
Mm-hmm.
A lot of folks still use it. A lot of folks use it, like I said, in transmission lines where the height of your shield wire is, a handful of feet taller than the height of your transmission line.
Right.
So.
Okay.
All right. So sorry about that tangent, but getting back to this. Again, this is the strategy. We roll up and over,
right, and
anything that falls inside this area underneath the sphere is considered protected. All right, so we have a 3D animation of this that I want to show you that we made that kind of helped better illustrate that. Right, that was showing you in 2D. So here's a nice 3D animation, and what we have here, we've got 100-foot mast with a 100-foot wire. We ignored sag of the wire, but there's a 100-foot wire to another 100-foot mast.
Mm-hmm.
Okay, and this sphere, this is I think a 100-foot radius sphere, is going to roll around. Now, this I asked our animator to create a substation, but they kind of did this at a poor scale. This is much smaller, so ignore the fact that this is a substation, but pretend it's just a single piece of equipment because that's about the scale of it. But we're going to roll the sphere, and every time we hit a shielding electrode, whether we hit a mast or a wire, we're going to stop the sphere and go around it, right? And it's going to create some zones of protection.
Okay.
Right? You can kind of picture already the zones of protection, but here we go. So in 3D, you can see this kind of, I like to call this a tent shape.
Right.
Right? You've created this kind of tent shape zone of protection. The sphere could not get through the wire. Right?
Right.
And you can see here these two buildings, right? One building falls completely under the zone of protection.
Right.
Whereas this building, part of it sticks out.
Mm-hmm.
So this part of the building would be considered exposed.
Right.
Okay?
Okay.
And so that's what a shield wire would look like. And then this is showing us what a single mast would kind of look like. I like to call this shape a witch's hat, right? So it's kind of reminds me of a witch's hat.
Yeah.
But that's generally the shape that you would get, and you can see, like you mentioned earlier, is very similar to the cone shape.
Right.
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 So, all right. So that should give you an idea of the kind of shapes you can generate.
Yeah.
Protection wise. But so let's any questions about those shapes?
No.
Pretty good.
Yeah.
Pretty straightforward there.
Mm-hmm.
This is your question earlier.
Right.
Right. What stroke current do you use?
Yeah.
You asked me. You said, okay, well this is the radius of the sphere. That's great. You told me it's based on the stroke current. Well, what stroke current do I use? Well, the answer to that, there's a couple of answers to that. In substations, this is probably the most popular answer for that question. We want to choose a stroke current that's associated with our insulation. Now, why is that? Our insulation, has a BIL, right? The
Right.
insulator. You have for example, you have 230 kV bus, and according to our charts here, a 230 kV bus has to have an insulation level of 900 kV. Okay, that's pretty standard, right?
Right.
So what does 900 kV mean, right? That 900 kV is the maximum amount of voltage that the insulator can withstand before it causes flashover to the bus. So that bus is at 230 kV, but if there was an impulse, such as a lightning strike, that would cause the voltage of that bus to exceed well over the 230 kV, let's say it causes it to go up to 900 kV, then if you put 900 kV of voltage on this bus, then it would cause flash over that insulator. It would flash over that insulator, and cause damage to the insulator, cause damage to whatever, right?
Right.
So, and that's a situation that we want to avoid.
Okay. Right.
So, anything less than that 900 will just be absorbed by the system. It won't cause flashover.
Right.
So it's not considered a problem.
Right.
Right. Now, will it cause some minor issues with the electronics? Maybe that's possible, but for the most part, the equipment can absorb it, and that's why we put those 900 kV insulators or whatever it is.
Yeah.
So that. And let me state this, that again, when somebody says 900 kV BIL, basic impulse level of that insulator, does that mean that 100% of the time a 900 kV or less amount of voltage will not cause flashover? No, right? I think to get those ratings, they mean like 90% of the time, but there's a lot of environmental factors that would contribute there. Yeah. Let's say that insulator is dirty, or it's wet, right? That may create a path for current. Or if we do a lot of work near oceans, right? The salt water from the oceans, or we do a lot of work near construction sites, the dust and things like that. All these things that can contaminate the insulator may cause that insulator to flash over much earlier than 900 kV BIL. Yeah. But again, nothing in lightning protection, nothing that we do is 100% short of the Faraday cage. So, but for practical purposes, we're going to assume, that the 900 kV BIL does what it says it'll do.
Right.
So what we do, that 900 kV BIL is associated with a stroke current. Now this ZS factor, this is the surge impedance of the conductor in ohms. Surge impedance is basically a factor of the height of that conductor and the radius of that conductor. Those are fixed items. You'll know what your bus height is. You'll know what your conductor radius is, and you could fill that out, and you could get the stroke current. Now these numbers actually change IS very small. They have a very small factor. The biggest factor is going to be the BIL. Okay. Yeah. So this is how we calculate stroke current. So you would plug in 900 or whatever your BIL is here, and then whatever your surge impedance based on your conductor height and your radius in here, and it would come up with a stroke current to use. Right. Now that stroke current would be the stroke current that just causes flashover of your insulator. Okay. Any current less than that, we're not worried about. Right. Because your insulator will absorb it or whatever. It won't cause flashover. So any current less than that, we're not worried about. Now, makes sense. And real quick here, for stroke current, for BILs less than 350, I mean, we just typically just set the stroke current to 2 kA. Okay. And the reason we do that is 2 kA is a very, very small stroke current. It represents less than a 10th% of all lightning strikes. But once you get too small, it's impractical to do. But we'll get more into that. But again, the key takeaway from here is any stroke current less than IS, the IS associated with your BIL, is not an issue. It's not enough to cause flashover of that insulator. Okay. So what about stroke currents that are greater than IS? What do we do about those? So the key here is that stroke currents that are greater than IS, if you remember, will have a larger strike distance. If I raise IS, I've raised my strike distance.
Right.
So those stroke currents are going to be associated with a larger sphere.
Right.
It's going to be a step leader that has longer reach.
Right.
Right? So if I can protect against the really small spheres, I can protect against any sphere that's larger. Because a sphere that has more stroke current has more reach.
Right.
And if it has more reach, it's more likely to reach a shielding electrode, a mast, or a wire versus reaching my equipment.
Right.
So really, the worst case strokes are the small ones,
right,
not the big ones. Again, the bigger ones have more reach and are therefore more likely to hit a mast or an electrode.
So you're just going to use the smallest sphere.
Right. So we want to use the worst case sphere is the smallest sphere.
Right.
But if it's really small, as we said, if it's really small, it won't cause flashover. So we want to know what is the smallest sphere that just causes flashover.
Right.
Right. And that's our worst case sphere, and that's what we've identified here.
Right.
Again, if you think about a system of masts and wires, and we're using this rolling sphere to protect it, and we get it so that this rolling sphere can't enter our equipment. We've put our masts and wires in a way that the rolling sphere can't fit into our equipment. We know that if the sphere was bigger, it also can't fit. Right?
Yeah.
If we can protect against a small sphere, we know we've protected against any sphere bigger than it.
Right.
Right.
Yep.
So that's the idea there. We want to find the smallest sphere, just as you said, that just causes flashover. That's the dangerous one.
Makes sense.
So, all right. So let's talk more details about the sphere and some observations. Okay. So the first one, if the stroke current is larger, protection is increased. Right? We just talked about this, right?
Right.
In this example, IS maybe is the blue, represents the blue sphere, and if we made IS larger, you make S larger, right? And if you make S larger, you gain protection, right? If the area under the curve represents what's protected, you can see the area under the red curve is much larger than the area under the blue curve.
Right.
Right.
Yeah.
So again, if we can protect against the blue, we know we've definitely protected against the red.
Right.
All right. And you remember this picture, same illustration here. We said that this piece of bus was in danger for a step leader forming where this red X is, because a step leader here cannot quite reach the mast, but it can reach this equipment.
Yes.
But what if that's assuming that the stroke current is exactly the magnitude associated with this blue circle.
Right.
What if in reality the stroke current is a little bit bigger? Right? If it's a little bit bigger, now it can reach the mast.
Right.
And now this stroke current, a stroke forming at the origin point of this step leader, is no longer dangerous. That if it has this magnitude of the red circle, it will strike the mast instead of striking this bus.
Right.
Right?
Yeah.
So this is only dangerous for a step leader forming in this exact location and with this exact magnitude.
Right.
So you can see how, if you remember in the fixed angle method, something that fell outside the protection zone, we would have said, well, that's unprotected.
Right.
Well, we realize it's unprotected for that exact special case scenario.
Right.
But if the scenario were changed a little bit and the actual stroke current magnitude that occurs in nature is actually a little bit bigger, then we would be protected from that.
Right.
So that's an important distinction. Okay. And we're going to get even more detailed about that a little bit later. The optimum mast and wire height is S. Okay, so if S being the radius of the sphere.
Right.
Right. So if I'm choosing a mast or wire height, I want to choose one that is equal to the radius of the sphere.
Right.
Because that'll stop the sphere, with the most amount of area under the curve.
Right.
Right. Now, a mast that's taller than S has no effect, but a wire that's taller than S can actually reduce protection. Now, let me show you why. If we raise the mast, previous picture the mast was here, it was at the diameter of the sphere. We've raised it. It did not stop the sphere any earlier. It stopped the sphere in the exact same place.
Right.
However, if we raise the wire from here to here,
right,
we can actually reduce protection, right? The new protection is only under this red circle. And why is that? That's because the sphere began to roll underneath the wire, right? It can't roll underneath this, but it can roll underneath a wire.
Right.
Now, people tell me I'm a little paranoid when I talk about this, but if you remember the video, we saw some of the step leaders moving sideways.
Yeah.
Right. So we can't guarantee that everything's coming top down and is going to find this wire. It may be coming from the side, and that's why we do the rolling sphere from the side as well.
Okay.
Right.
Yeah.
So this is a common mistake a lot of people make. They have trouble with their protection. So their protection zones, they say, well, it fails. Oh, just raise the wires.
Right.
While that is a great solution most of the time, you got to check. You got to make sure that you're not raising the wires to a point that you're causing the spheres to sneak in underneath it.
Right.
So, all right. The height of the equipment can affect the radius of protection given by a mass. All right. So first off, what is radius of protection? If you remember, the radius of protection is the distance away from a master wire that I can put some equipment.
Right.
If you remember the empirical curves, I believe there was a factor, a horizontal factor. I think it was 8. I think it was X.
Yes.
Right. The horizontal factor X.
65 feet.
Right. That's right.
Yeah.
And that tells you how far away you can put your equipment. So, if this is the sphere and this is the mast, you can see that taller equipment has a reduced radius of protection versus shorter equipment.
Yeah. It's kind of the brim of the witch's hat.
There you go. Yeah. That's exactly right. So we're getting closer to the brim away from the center.
Right.
So if we are shorter, if our equipment is shorter, we'll have more radius of protection, meaning we can put our equipment further away. So this is something that we can calculate, right? We have the formulas, we have the geometry. We can calculate what this R is based on a given equipment height. And then we know, we're given a strategy. As opposed to just randomly putting mass and wires out there and seeing what we get, we can have some idea of, if I put my equipment within R, then I know I'm good.
Right.
And this is also important because as you protect a substation, you're going to have several different equipment heights. Right. Some equipment may be 20 feet, some other equipment may be 30 feet. So you really should do a protection calculation for different heights.
Yeah.
Now, if you choose the highest point of your substation, if you choose, let's say 30 feet is the tallest bus that you have in your substation, and you're able to protect your entire substation, assuming everything was at 30 feet, and not everything's at 30 feet, it kind of goes back to the sphere. You know that if you've protected against 30 feet, you've protected against shorter equipment as well.
Right.
If you've protected for equipment that's 30 feet tall, you know that equipment that's actually 20 feet tall will fall under that protection as well. So that's a way to simplify calculations, is just going for your highest equipment. However, if you go for your highest equipment and you have to put up a lot more mass and wires, you may not be giving yourself credit. That may be too conservative an assumption, and then you're going to want to eliminate some of those assumptions to save some money for your client on the mass and wires, and that's very important. We want to be economical with the number of mass and wires that we choose.
Right.
So, just some strategies to think about. All right. Also, BIL and conductor effects affect the strike distance, right? So, again, I told you about this surge impedance formula. I didn't show it to you before, but here's the height of the equipment and the radius of the conductor.
Okay.
And then if you have more than one conductor, you're supposed to use the equivalent radius, and these are some formulas for that.
Okay.
But the point with this is your strike distance and your protection is affected by your BIL, greatly from your BIL, because that affects your stroke current, it affects your strike distance. And it also is affected by the conductor height and the conductor radius.
Okay.
So if you wanted to do this properly and in great detail, you should do a different calculation every time you have a different conductor height, every time you have a different conductor, every time you have a different radius of conductor.
Right.
That would be the most detailed way to do it. Now, it's not always practical. It often doesn't change the results.
Yeah.
But BIL will definitely change the results, right?
Right.
BIL, like I said, these things have a smaller impact, but BIL has a large impact.
It's the most important factor.
Yeah,
Okay.
it's the factor that one step can change it significantly. So you probably, a good strategy, and you'll get a feel for this. This is more of an art than a science, but you'll get a feel for it as you calculate your protection zones. You definitely want to do a different sphere, a different calculation every time you have a different BIL in your substation. But every time you have a different, and maybe every time you have a different conductor height, if there's a significant difference. But when it comes to the conductor itself, the radius of conductor, that has a negligible difference in it. But again, to follow the guide properly, you would do that. But what I like to do, I like to find out which radius of conductor would give me my worst case, would give me my smallest sphere, and use that one, knowing that conductors that give me a slightly larger sphere, I protected against those if I protected against the smaller sphere.
Right.
So just a way to kind of reduce some of those calculations.
Okay.
So, any questions about what we went over there with all the different kind of gotchas and all the different analysis there?
No, I think it makes sense. Yeah.
Okay, good. So let's now, what we want to do, we want to get into the radius, some of the geometries of protection.
Okay.
So let's do that. Let's see. All right, we'll pick up from here. So again, this is just to help show you some of the shapes. This is a section view. Okay, this is a massed section view, and this is the plan view. This is the bird's eye view, top down. So the zone of protection you'll get, this is that witch's hat, right, that we talked about, and this is also that witch's hat here, but at the equipment height. We want to know what is the protection at the equipment height. So it'd be a cutoff witch's hat, right here. This would be the section view of that, and that's reflected here. So that's pretty basic. As you roll the sphere around this is what it looks like from the side. This is what it looks like from the top, as far as your protection zone. Yellow being your protection zone. Okay, and that's given by these formulas. The radius of protection is given by this. Again, now we said for HM greater than S, whereas for HM less than S. So this is HM is the mast height. Okay. Right? When the mast height is less than S, you have this formula. When the mast height is greater than S, you have a shortened formula. And the reason for that is, if you remember, once the mast height gets above the radius of the sphere, it doesn't change anything. The sphere still stops at the same point. So we've eliminated that that part, that change, and we basically, for a mast that's greater than S, it's just essentially there's no HM here, right? Okay. We just assume S is the height of the mast. Yeah. But again, we don't want to get too deep into formulas here, but I just wanted to share with you a few observations of it. So the shield wire, okay, this is the red dot represents a wire going into the page. Okay, again, this is the elevation view, and this is the plan view. Okay. You can see it gives us that tent shape that we got in that 3D image before. Yeah. Right? So you can kind of get a picture for what this is going to look like. Now, as you can see, you're going to, a lot of people ask me, well, you're going to need mass and wires all over the place because the amount of protection you're getting doesn't look like very much. Well, and that's where the combination of protections becomes so important. For example, if you have two masts, right? Let's say this is the plan view again. We have a mast here and a mast here, the two red dots. Right. Okay. Individually, they provide this protection. Right. Right. But together, they provide this bonus protection. Oh. Right. Because the sphere cannot squeeze between the two masts. Huh. As you roll the sphere around, it cannot squeeze between the two masts. Yeah. And it's dictated by these formulas. And therefore, you get this bonus level of protection by having two masts kind of close together.
That's interesting.
Yeah, it's interesting. And remember, The fixed angle method, we talked about that.
Mhm.
We talked about if you have two masts that are kind of close together, instead of 30 degrees, we increased it to 45 degrees, right? And that was based on observation,
right. Yeah.
So this kind of explains why.
Yeah.
Right. This kind of
Yeah.
explains why when two masts are kind of close together, you get bonus protection.
Okay. Yeah.
And so here you get that bonus protection, which is significant. This is actually a lot of bonus protection, a lot of area.
Yeah.
Okay. Now imagine two wires. Okay, so you have
Okay.
two wires running across your substation. Individually, they provide the yellow protection,
Yeah.
but together, they provide this bonus green protection,
Right.
right? And this is because this is the section view of it, right?
Yeah.
If you have two wires,
Yeah.
as long as those wires are close enough together to support the sphere,
Yeah.
then the sphere can't go below that wire, right? So
Huh.
it basically holds the sphere up along your whole substation.
Yeah.
Now, this is by far the most economical and the most popular way to protect a large a substation,
Okay.
right? You basically, on your dead end structures, your outside dead end structures, you run a wire from your high voltage structure down to your low voltage structure, and you do it again from this high voltage structure down to this low voltage structure.
Right.
And as long as those wires are less than, a little bit less than the radius of the sphere,
Yeah.
you're going to hold that sphere up the whole way.
Yeah.
And now, if just because they're exactly the radius of the sphere, or just less than the radius of the sphere, I should note that the farther you spread these two apart,
Mm-hmm.
the lower the sphere begins to droop, and
Right.
eventually it cuts into your equipment height.
Right.
Your equipment may be this tall or whatever it is, but as long as the two wires are close enough together to not allow the sphere to cut into your equipment height, everything between those two wires is protected.
Yeah.
So that's pretty cool.
That is.
Now this is three masts. Okay, so here we have a mast here, a mast here, a mast here, and we would treat this calculation the same as we did the two mast calculation.
Right.
We would do the two mast calculation for these two masts,
Mm-hmm.
we would do the two mast calculation for these two, and we would do the two mast calculation for these two.
Okay.
And we would gain these green bonus protection area.
Right.
However, one thing to consider is when the sphere rests on top of the three masts, it's possible for the bottom of that sphere to cut into the equipment height.
Okay.
Okay?
Yeah.
We can't just assume everything inside the triangle is protected. Right?
Right.
We've created this bonus of protection, and we've defined a curve here. We've
Yeah.
defined a curve here. We've defined a curve here. But the sphere can't go in here. But if the three masts are positioned just so that the bottom of the sphere cuts into the equipment height, is possible to have this area, this unprotected area, or this exposed
Mm-hmm.
area. Now, I've done a lot of these calculations, and man, 9 times out of 10, this is not the case. I mean, it has to be
Mhm.
just right. But it's important to note is
Yeah.
you got to check
Yeah.
for it. You got to check for it each time and make sure that for as you do this calculation of B, you got to make sure that S is indeed less than or equal to B, so that you can say that this area is 0.
Right.
Otherwise, it may have some area that you got to consider.
Right.
So,
Okay.
same thing with 3 wires, right? If you
Right.
have 3 wires and the sphere is resting on top of those 3 wires,
Yeah.
okay. Now this blue circle does not represent the sphere. I should clarify. I guess in a way it does here, but here it represents more of like the contact points and things like that.
Yeah.
It represents this R.
Okay.
Okay, but anyway, that's diving deeper into the formulas than we need to get into right now. But same thing. If you have 3 wires, you can do the wire radius calculation for a single wire and do that all the way around.
Right.
But you got to check to see if when the sphere is resting on top of the 3 wires, will it cut into your equipment height? And that's
Right.
done by this formula.
Okay.
This occurs a little bit more often in my experience than this. I mean, again, it's according to just where they're placed, but but at the same time, it's very rare that you see this kind of triangle-shaped 3-wire shape in a substation, though it does happen.
Okay.
So those are the combination protections, and you can see you get a lot of bonus protection when you use these combinations versus just the single wire and single mast here.
Right. Yeah.
Right. Any additional questions about this section?
No.
Okay. All right. Well, with that, do you want to take a quick break? You want to continue? We can continue talking about failure rate.
We can continue.
Okay. Great. Yeah. Let's continue then. So failure rate. Now, so we've defined all the zones of protection and how to define whether something is protected. But what if that equipment lies outside those tents or those witches' hats? What if that equipment falls out of our zones of protection? What do we do? Do we, try to protect it, or is that always economical? A failure rate calculation will show us exactly how many strikes we can expect for that area, and then we can make a determination whether we need to add shielding protection or not.
Okay.
So to do that calculation, if the equipment lies outside of the protection, then you want to determine the minimum strike distance that would have resulted in protection. Remember, our sphere was defined as the worst case sphere, the smallest sphere.
Right.
Now, the smallest stroke current that causes flashover.
Yeah.
Now, is that the actual stroke current of a random given lightning strike? Probably not, right?
Right.
We don't know what it's going to be. The actual stroke current may be greater, may be smaller, and the BIO will absorb it. We don't know. We've just defined our sphere based on the worst case.
Right.
So we want to know, well, okay, if that was worst case, how much larger should my stroke current, or would my stroke current have been, and that equipment be considered protected? Let me rephrase that. If my stroke current was a little bit larger, would my equipment have been protected?
Right.
How much larger does it need to be for that to be protected? Right. That's what we're asking ourselves here.
Yeah.
And that is the stroke current ISM. All right. In other words, if my stroke current in reality is ISM, then that equipment would be considered protected because the sphere would have been large enough.
Right.
And it would have reached a shielding electrode instead.
Okay.
So we determine what are the chances of that strike happening, and then we calculate the probability that a stroke will fall in that window. Okay, IS being the dangerous stroke that just causes flashover, and ISM being the stroke current that is safe, the stroke current that our equipment would have been protected, the stroke current that we would have reached a shield wire or a shielding electrode. Okay. And then, so what is the window of strokes? What is the probability that a strike occurs in that window between IS and ISM? Okay. So, great. I should have used these illustrations. So again, going back to this example, right? We decided that a stroke current associated with this blue sphere would have been dangerous here.
Right.
But a larger stroke current might be safe.
Yeah.
So only stroke currents that are less than the red sphere but greater than the blue sphere are the stroke currents that would be dangerous.
Yeah.
And what is the probability that the actual stroke current falls in that window?
Right.
And that's what we want to calculate.
Okay.
And we can calculate it with these formulas. All right, these formulas are out of IEEE. And there's two formulas for this. I think there's one where this constant is, I believe, 31 instead of 24. Okay. But again, this will give us the probability of that. Now this gives us like a half bell curve that shows us the probability of natural lightning strikes based on observation.
Okay.
So from that, we can then calculate the probability that ISM will occur,
right,
the probability that IS will occur, or strokes greater than IS and strokes greater than ISM, and we can find the difference. And that will tell us the probability that a stroke falls in that dangerous window.
Okay.
Okay?
Got it.
All right. Then we want to measure the area of that unprotected region. Okay, and because that area will be added to a formula, and then determine the number of expected strokes in that area. Okay, so this is from the National Weather Service. This is called a chronic level map or isochronic level map. Okay, and what this represents, you see a bunch of numbers on this map here.
Yeah.
The numbers represent a thunderstorm day. So if thunder was heard that day, it got, so someone counted it.
Okay.
Right. So out of a year, this is how many days will have at least one strike of thunder or strike of lightning or heard thunder. Right. So out of 365 days in a year, we can see that this line, 60 out of those 365 days a year will experience or experienced thunder.
Right.
Right.
Okay.
Now that could be one lightning bolt. That could be 100 lightning bolts. It still counts as one.
Okay.
Right. So it's not perfect. It's not great. It doesn't tell us really magnitude difference. Now I will say this: the new version, the 2012 version of IEEE 998, actually has flash density maps, like 10 years of data flash density maps, and we've included that in there. And that gives you a better idea for if there's several strikes during that day, would be weighted a little bit heavier versus only one strike that day.
Right.
So that's there.
Okay.
But again, for our purposes, this is very accurate. This works very, very well.
Yeah.
Now, a few things you'll notice. This is the Tampa area.
Right.
They have some of the most lightning on the planet. So this means
Wow.
out of 365 days, 100 of them have lightning.
Don't want to live there.
Yeah. Well, whereas in Southern California, you can see they have 5 or less days out of 365.
It's interesting the variation. Of course, Tampa has good beaches. It's a good reason to live there too.
Oh, so that's very true, right? You might survive a few lightning storms and enjoy the weather. Right. But certainly Southern California, California out west, they don't even put shield wires on their transmission lines.
Huh.
Right? You build a transmission, it's not worth it. They experience so little lightning.
Yeah.
As it is 5 days a year, they actually have lightning.
Yeah.
That why spend the money on transmission? It's not worth it to them.
Right.
It's more dangerous that the shield wire could fall off and short your bus. That's more likely to happen than actually getting struck by lightning.
Wow.
Yeah.
Interesting. So it looks like most of the southeast is around 60-ish or so.
That's right. So and let's say you had something in Atlanta, Georgia, right? What number would you use?
60.
Yeah, I'd use 60 to be conservative.
Right.
We know it's probably like 55 or something like that.
Right.
But to be conservative, I would always go with the bigger number, and I would just use 60. So.
But if you're in Blairsville, North Georgia, you might go with 50 or.
Well, I would. You probably want to go like 55 or something like that.
Okay.
It's safer to go 60. If you're having problems at 60, like if you plug 60 in and you're getting a result that you don't like, you've made a conservative assumption. We know it's not 60. We know it's something less than 60.
Yeah.
But 60 caused failure. 60 caused failure.
Yeah.
Will 55 cause failure? It's unlikely that number would affect things greatly.
Yeah.
But
like say between Macon and Florida border, you might conservatively go with 70.
Yeah. So if you're in this area, I would go with 70.
Yeah.
Whatever area you're in, look at the two lines that touch it and go with the bigger one.
Right.
That's usually safe, unless you're just like right on the line or something. Then you can go with the smaller one. That's the way generally I use that number. But anyway, what we're going to do, we're going to take that number. That number is T. Okay, and then A is the area we measured in the previous step, right? The area that's exposed, the area that falls outside the tents or the witches' hats.
Yeah.
The area, that area we're going to multiply by T and multiply by this factor, and then that's going to give us this number N. Okay. So, and then take that N and plus our probability that a stroke causes failure, which was given in this previous step, right? Given that a strike has occurred, what is the probability it falls inside that window, right?
Right.
That's what that probability is.
Yeah.
And we're going to apply this formula, and that's going to give us our failure rate.
Okay.
Right? So how many failures we can expect per year. Right. Or, and these numbers are very, very small decimals, and it doesn't always make sense to say you're going to have 0.0005 failures per year. Right. We typically take the inverse of that and say, one failure every so many years. So you can
Okay.
expect one failure every maybe 100 years, failure every 500 years, something of this nature.
I see.
Right.
Okay.
So and as far and that determines, so when we're given a design, our clients will typically give us a criteria, a design criteria. They'll say, design a lightning shielding system that gives me a failure rate of one failure every 100 years or better. Right?
Right.
So if we get one failure every 100 years or better, we've met our goal. If we
Right.
don't, then we need to go back and look at those unprotected areas
Right.
and maybe add some mass or add some wires in there.
Yeah.
So again, so just because something falls outside of a witch's hat doesn't necessarily mean it's a bad thing.
Yeah.
If we can still achieve our failure rate, then maybe that's okay. Now,
Yeah.
if in some cases, a lot of these utilities have very cheap methods of adding shielding mass. Some use steel, which is a lot cheaper than concrete. Maybe they
Right.
live in an area that doesn't have a lot of hurricanes, and so they can get away with steel. So
Right.
they may want a higher failure rate because they know economically it's pretty cheap for them to add a mass.
Right.
Whereas if you're in an area that uses concrete, maybe an area that has tornadoes tornadoes will blow everything down, but higher wind speeds because of hurricanes or what have you, or soil reasons. For whatever reason, if they're using concrete, then they may say, well, we're willing to accept a lower value of failure rate because it costs a lot of money for us
Right.
to put in a new mass.
Yeah.
So that's some considerations. Another consideration is, this is probably the biggest question I get all the time is what failure rate do we use, right?
Yeah.
And it really, it's really up to the utility, and it depends on that substation. If you have a critical substation that's feeding a lot of other tertiary substations,
Right.
right? That one you may want a failure rate like 1 in 500 years or something big.
So you want a lot of protection.
Right? You want a lot of
Yeah.
protection. You want to make sure that stuff doesn't fail.
Yeah.
Right. Whereas if you have a substation that there's nothing else down the line, it's not critical infrastructure. You may
Yeah.
be willing to accept a failure rate of like 1 in 100 years or something
Right.
like that.
Not worth spending the money to make sure that failure
Right.
never ever happens.
Exactly. Is
Yeah.
it practical to do, and it may not be worth it. So
Right.
it all depends on the economics of those things, and that's something that we work with together with our clients to help them determine what those failure rates are. Generally speaking, I like to say, define at least 2, if not 3 categories of priority substations. And say priority 1, our top priority substations cannot go down. We need to have 400 or 500 years between failures.
Right.
And then and then you may have priority 2 and then priority 3. Priority 3 being the lowest priority. If these things go down, there's a lot of backup. It's not going to cost us a lot. We'll accept 1 failure every 100 years.
Yeah. That makes sense.
And then that
Yeah.
may be better.
Yeah.
So and if a substation is going to expand, that's something to think about too. Let's say you've got a substation built and you've got it to 1 failure every 100 years,
Right.
but you've only halfway built the substation.
Right.
And 10 years from now, you plan on expanding that substation to double the size of it.
Right.
And, you put in the same level of protection. Well, you have 1 failure every 100 years in the old half, and then let's say you have 1 failure every 100 years in the new half.
Right.
As a whole, your substation now has 2 failures every 100 years.
Right.
Right?
Yeah.
So if you have set your failure rate to 1 failure every 100 years, and that substation is going to expand,
Right.
as soon as you build something else, you've gone over
So
that.
you have to plan for the expanded substation
Yeah.
from the beginning.
Plan for those expanded substation, or maybe what's more a better way or practical way of doing it is set a higher failure rate that has some window, and then every time you expand that substation, you gotta reassess. You gotta reassess the whole
Right.
station.
Right.
And see what the failure rate is of the whole station.
Right.
So that's important. So, any questions about that?
No.
Okay. All right. So let's continue on failure rates. Okay. Well, that's it. Well, that's it for failure rates. But now I briefly want to go over some common mistakes. Now, we'll fly through these, but I've been doing this for a number of years, and I've seen where people kind of maybe learn this halfway and apply some of the concepts improperly.
Okay.
So mistake number one, expecting 100% protection. What's wrong with this?
Well, lightning is a highly probable thing, and so you can't ever get 100% protection.
Absolutely. Lightning is, if you get nothing else from this class, lightning is a highly probabilistic phenomenon, and we do not have the science to know exactly what lightning is going to do every time, right? All of our formulas, all the formulas you just saw, are based on some level of probability is interlaced into those formulas because they're all based on observation. So even IEEE 998 says this, right? There is no known method of providing 100% shielding short of enclosing the equipment in a solid metallic enclosure. Right. Now, this is important. I have seen, the reason I put this in here is because I have seen a utility standard. I'm not going to name the utility, but I've seen a utility standard that said, okay, for our sensitive, expensive equipment, such as transformers and breakers, we want 100% protection. All other things can have a lower level of protection, but for transformers, we want 100% protection.
Right.
That's not practical. You can't do it. You can't protect against every static electric, shock, and nor is it worth doing. So,
right.
So again, it short of creating a Faraday cage, you're not going to be able to protect everything. So that is mistake number one.
Yeah.
So how do we resolve this? Well, we resolve it by calculating a failure rate. Instead of saying 100% protection, we talked about this failure rate. We can say, well, we can't guarantee 100% protection, but we can say you can expect one failure every 100 years. Or one failure every 400 years, or whatever it is, in this area. Yeah. And let me make a quick point. Those sound like big numbers, right? I don't know about you, but I plan to retire in the next 400 years, right? So I'm not gonna be around.
Hope so. Yeah.
But now, does that mean you're really only gonna have one failure every 400 years? I mean, I guess yes, technically it does, but remember, there's other reasons for failure. There's other reasons other than the strike just getting into your shield. Into your shielding system. Somehow the sphere magically getting, into your shielding system. You could still have failure of your insulation. We talked about that.
Yeah.
You could have where lightning, again, we said lightning, this failure rate is based on lightning always striking the mast instead of striking your equipment. Yeah. And we know that that's not always true. Right. So these things will actually reduce that actual. So when you say 1 in 400 years or 1 in 500 years, what we're saying is the sphere, or we're saying the exposed area will get struck 1 in 400 years or 1 in 500 years. But the quote-unquote protected area, where we don't know how often that's going to get struck. According to this method, we're saying it's not going to get struck at all, but we know that's not true. We know that it can still get struck because it may have insulation failure, or it can still get struck because for whatever reason, the step leader chooses to strike the equipment instead of striking the more attractive shielding electrode. Maybe you have bad grounding in the area, and that grounded shielding electrode is not that attractive. A number of different reasons. So when somebody says 1 every 100 years or 1 every 400 years or whatever that failure rate is, they're referring to only this exposed area.
Yeah, right.
So, all right. I'm going to call this mistake 1B. Okay, this is misreading a report and assuming zero protection for unshaded areas. So let's say we do a lightning design, okay, and we've created a plan view and we've shaded all our areas that fall under tents and fall under these witches' hats and all this stuff. We've shaded all this. Yeah. All right. This is kind of the opposite problem. Just because something is outside of that shaded area doesn't mean it's unprotected. Right. We can see from here, had the actual lightning strike, or if the actual lightning strike is greater than this minimum strike that would cause flashover. Yeah. Which it probably will be. It's doubtful that it's going to fall exactly the number that's going to cause flashover. Yeah. If it's a little bit larger, we are protecting against that strike and bigger. Right. Yep. So I don't like to use the word unprotected for that reason. I prefer using the word exposed because it's not it's not unprotected. We are providing some level of protection, just not as good.
Right.
We're still protecting against bigger strikes.
Right.
We're protecting against the red circle. We're not protecting against the blue circle.
Yeah.
So it's really exposed.
Right.
Any questions about that?
No.
All right. So again, when you read one of our reports, or if you happen to be a client and you get one of our reports and you see, hey, this area is not shaded. Oh no, it's unprotected. No, that's not necessarily the case. So, all right. Mistake number 2: using the BIL method to protect against to protect equipment not separated from ground by insulation. So remember, BIL, the BIL is the insulator, and we're talking about how we use the BIL method to help us determine the stroke current that's associated with flash over that BIL.
Right.
And then from there we determine our sphere radius.
Right.
Right? So what about equipment that doesn't have a BIL? Is there some equipment that doesn't have a BIL? Can you think of anything? How about the tank of the transformer?
Right.
Right. The transformer has a BIL, right? The bushings have a BIL.
Right.
But the tank itself, the oil tank, that's grounded.
Right.
It's not separated from ground with an insulator. It doesn't have a BIL.
Yeah.
The control house. What about the control? What about the breaker tank? Right. There's a lot of equipment in the substation that doesn't have a BIL.
Right.
And if it doesn't have a BIL, should we really be using the BIL method to determine the stroke current? And I would say you really shouldn't. You can, and that's going to give you a very good calculation, because the BIL method does provide a pretty conservative number for your sphere.
Yeah.
But if we want to do this properly, we shouldn't think about it that way.
Right.
Okay? Instead, what we should do is that probability method. Okay. If you remember, I showed you this formula before, and I told you that there's two guys debated this formula, and one guy said this constant was 31, and the other guy said it was 24.
Right.
Okay. The way this formula works is you plug in a value of probability that you want to solve for, or that you want to protect against. So let's say you want to protect against 99% of all strikes. You would plug in 99% in P of I.
Right, and this is for, say, your transformer.
Right, for your transformer or something like that. Right? Well, not for your control. We'll get to the control house in a second, but let's say your transformer tank, things that aren't separated from ground with a BIL that you don't want to experience direct strikes.
Okay.
Right? We can't say, well, there's a minimum value that won't cause damage. We're assuming all strikes cause damage because there's no BIL to absorb the strike, right?
Right.
So we would plug in 99% and solve for I.
Right.
Right, and we could do that with this formula or this formula. This one's a little bit more conservative. This will give you a smaller sphere radius, right? That will result in a little bit more difficult to protect against. But both formulas are in IEEE 998, and both formulas are good. But here's a chart of that formula. So when you plug in 99%, you're going to get some value. What value are you going to get? I don't know. Let's say you put in 99% here. You may get 10 Ka.
Right.
Right. You may get 10. What this means is, this is the probability that a given stroke, a random given strike in nature, is equal to or greater than this stroke current. Okay. Remember, it's not that we care about what is the exact stroke current. We care that the stroke current is this amount or greater. Because if it's greater, we know we have a larger sphere, we have more reach, and so if we can protect against stroke current X, we can protect against stroke currents that are greater than X.
Okay.
So as you can see, how much percent of stroke currents, how much percent of lightning strikes are greater than 0 Ka? 100%, right? All of them are greater than 0. Okay, and then you can see 99% of them are greater than 10, right? And then you can see how much percent are greater than 20, and so on. So you can see, what I like to do when I have something that doesn't have a BIL, I like to put 99% in here and see, what that exact number is. I don't know it off the top of my head, but again, put 99% in here, solve for I, and you'll get something around, 9 or 10 Ka.
Yeah.
And then I would use that number to then determine what my sphere radius is.
Okay.
Okay, and I'll use that and roll around the sphere, roll around the sphere around the substation, and say, okay, you're protected against 99% of strikes, or whatever. Everything that falls under the witches' hats, everything that falls under those zones of protection, are protected against 99% of strikes.
Sounds fairly simple.
Yeah. Any questions about that?
No.
But these are the same probability formulas that we used earlier in the failure rate calculation.
Yeah.
When we were trying to say, given any given strike, what is the chances that it's going to be this stroke current magnitude or larger?
Right. Okay.
All right. So, this is, I got a note here. This is also good for the low BILs. So if you remember, we said if it has a low BIL, use 2 Ka.
Yeah.
That's what a lot of folks do. I actually prefer using this because if you think about it, if we use 2 Ka, 2 Ka accounts for some 99.5. It's going to be a big number.
Right.
Are we being too conservative, too picky here? That's possibly. So I always recommend, I'll always do what the client tells us to do, and it's unique to their situation, but I always recommend not going below 99%.
Right.
Okay. All right, now, you asked about a control house. Control house also doesn't have a BIL. Right?
Yeah.
So there's two thoughts on control houses. A lot of control houses are metal buildings. Right? So they themselves are metal, you've created a Faraday cage, which we just talked about as being protected.
Yeah.
However, though they may be considered Faraday cages, when lightning strikes that building, it's not an ideal Faraday cage. It's not a perfect Faraday cage. Okay,
Yeah.
You could still have some interruptions. You could have some issues. You got equipment attached to the walls. Sensitive electronic equipment. You talk about relays and communication equipment and all kinds of stuff. So what we do to protect, when someone asks us to protect a control house, we always refer to the NFPA 780 standard. And that standard basically says use a 150-foot strike distance. It just gives us the sphere radius.
Okay.
Right? And this sphere radius, we could back calculate it and see what percent of strokes it's covering. But this sphere radius is what the NFPA has said is what you should use for buildings.
Okay.
Right? Now, I think, there's a few special cases in NFPA. We do a lot of lightning protection for NFPA, using the NFPA method, especially for like our solar plants, right? We do a lot of work with solar.
Right.
And we use NFPA for solar. If you ever have, I think the one exception to this 150-foot strike distance, there's a handful of exceptions, but it's like special case buildings, like if you're housing ammunition or if you're housing a lot of explosives, right? You may not be willing to accept the failure rate associated with a 150-foot strike. That may be more dangerous. So they actually reduce your strike distance down to 100 feet for those special case buildings.
Right.
But for most buildings, use a 150-foot strike distance. All right, and this is what, I gave this training to Duke Energy a number of years ago, and they were gracious enough to allow me to take this photo and bring it in with their training. But this is how most buildings are protected. Is if you can see, look real closely. I don't know if it shows up in the video or not, but there's some spikes here.
Yeah. And
these spikes are 18 inches, 24 inches tall.
Right.
And the way they determine the separation distance for these spikes is based on a 150-foot rolling sphere.
Huh.
So a 150-foot rolling sphere would, be supported by this spike and this spike without touching this building, or maybe just barely kissing this building.
Right.
Right. So that's how they determine how far apart they can put these spikes.
But these on the right have to be closer together because you have a bit of an arch, right? Absolutely.
That's a very good observation. The reason these are closer together is because the sphere, if you take this one away, the bottom of the sphere would cut into that top part of the building.
Right.
Right? And then that building would be subject to lightning strikes, or that top part would. And they want the lightning to go here because this is connected to some sort of grounding system or down conductor that is then grounded. and it's much safer for the strike to go there as opposed to creating a fire or who knows where it's going to go if it was to strike here. So yeah, so that's why they added that extra one right there.
Right.
Was because of that art. Yeah. Okay, so mistake number 3: taller is better.
Right.
And we talked briefly about this earlier.
Yeah.
Remember, this video proves that step leaders can go sideways, can even come back up. You see some of these step leaders going up, certainly a lot going sideways. So we can't just assume top-down strikes for everything.
Right.
You know, that's not the right way to do this, is assume top-down strikes for everything.
Yeah.
So we talked about how the optimum mass wire height is S, but a mass taller than S has no effect, right?
Right.
However, a wire taller than S reduces protection. So therefore, the mistake taller is better. That's why it's a mistake.
Yeah.
It's a bad assumption. Again, you remember this?
Go underneath
Absolutely.
Wire. Yeah.
If you go taller isn't necessarily better. It could reduce. It may improve your top-down strike protection, but it could reduce your side strike protection.
Right.
Okay. All right. All right, mistake number 4. In dealing with multiple wires, taking the lower height to simplify calculations. Okay. All those formulas that I showed earlier, those geometry formulas, they're assuming when you have multiple wires or multiple mass, they assume that the heights are all the same.
Right.
Okay. There was only one formula for HE or one formula, HM for mast height, or HW for wire height.
Yeah.
You know, and those, you know, you can come up with the formulas, or you could model it in AutoCAD or 3D to find out exactly where the sphere would roll. But one thing that we tell folks that are doing this is when you have multiple mass, it's okay. Like, let's say you have 3 different mass and they're all 3 different heights. Just choose the lowest one, and that's a conservative assumption. Use that as your mast height. You know that in reality, the taller mass are going to prop that sphere up a little bit taller.
Right.
You have to be careful when you talk about wires, though, because with wires, if I just want to simplify calculations, and let's say this one and this one are my real wire heights,
right?
But to simplify calculations, I just say, well, we're going to make these 2 the same. We're going to make these 2 lower. Okay. This actually happened to me once. I was doing this for a client, and then I realized that by lowering this wire height, I've reduced the distance between these 2 wires.
Yeah.
And these 2 wires may support a sphere.
Yeah.
But these 2 wires may be greater than the radius of the diameter of my sphere. And the sphere could actually fall through.
Oh, wow.
Okay.
Yeah.
Now, again, you know, this is all highly probabilistic, and this is, you know, the chances of the step leader snaking its way exactly right there, probably unlikely. Right. But it is, you know, to do this properly, this is something to consider. You don't always want to just immediately lower your wire heights, because you've reduced the distance between the 2 wires and therefore made it more possible for these 2 wires to support a sphere. Whereas in reality, they may not be able to support the sphere. They're just something to think about.
Right. I guess if your client wanted more height for their device, then you may want to, you know, keep the higher wire as well, right? I mean, so that you can tell that there's more space under here of protection. Right.
There's more space of protection here. You mean? Well, I would never recommend to my client to like lower the wire.
Right.
Right. What I'm saying is, just as I'm modeling it, as I'm calculating it, for ease of calculation, to make the math easier, it's easier to just assume these are the same height.
Right.
But I would tell them, if my client has a wire here, I would probably say, you know, probably keep that wire there. I'd have to look at this side strike coming in and making sure that it doesn't roll underneath. But yeah, I would probably keep the taller wire height.
Yeah.
I just wouldn't. It would be wrong of me to do the math assuming that the wire heights are the same.
Right.
At least without checking to make sure that this distance, as long as this distance is less than the diameter of the sphere, I know the ball's not going in there, right? I know the sphere's not going to be able to fit in there. So, but I would just check, make sure this distance isn't greater than the diameter of the sphere before assuming a lower height.
Right.
All right.
Yep.
Okay, mistake number 5, setting a failure rate that's just too high, or trying too hard to meet a target failure rate. I'm not sorry about my English here. Setting too an impractically high failure rate. So I've got something mixed up there. But setting an impractically high failure rate, too high a failure rate. So if you set something 1 every 400 years, 1 every 500 years, make sure that it's right, for your case, for your substation. Again, the 400 years is referring to, or whatever your failure rate is. When we say 1 in 400 years, that failure rate we're referring to is the chance of striking exposed area. Now, we said there is also a failure rate inside the protected area, right? And that's not included in that failure rate, the 1 in 400 years. But you don't want to set something too high that's just too difficult to achieve, because again, lightning is highly probabilistic phenomena, as we said. It's also a rare phenomena. Mm-hmm. I mean, yes, it happens, in some areas of the country it happens more often than others, but for a given small area, it just doesn't happen that often. Yeah. So you have to be careful, and you have to put some engineering judgment in how big is my area, how important is this substation, what is the right failure rate to set for the substation, not let's just pick something really conservative and just go 1 in 1,000 years or something like that. Yeah. So, and then the next thing is trying too hard to meet a target failure rate. Okay. Let's say you do your lightning protection, right? Let's say you've done a study, and your failure rate, target failure rate, is 1 every 400 years. Mm-hmm. And let's say you do it and you've got 1 in 350 years. Right. Okay. If it costs you another $100,000 to put up a mast, or $50,000 or something like that, to go from 350 years to over 400 years, is that necessarily worth doing? Right. You got to think about it. Maybe. Yeah. Maybe, if it depends on the substation. Okay. If it's or it depends on company policy. Yeah. Right. If they say, hey, you got to have 1 in 400 years or 1 in 500 years, whatever that target rate is, and you've got to meet that target rate, by all means, meet that target rate. Right. But it's something to at least consider, because if you're putting a bunch of shield wires, let's say, and this applies mostly to shield wires. If you're putting a bunch of shield wires all over your substation, trying to meet a 1 in 400 year or 1 in 500 year failure rate, okay, fine. Yes, you've reduced the chances of lightning entering your system to 1 in 500 years. Yeah. But you've also made it very difficult because you have all these masts and wires around. Right? It's going to be hard to navigate that substation. It's going to be hard for equipment to go in and out. Now you've got all these obstructions in place. Yeah. What if you need to change out a transformer? You got a mast right next to it. Makes it more expensive. Right. It's going to make a lot of things more expensive. Yeah. What about, and let's not forget, shield wires themselves, as we talked about with California, shield wires themselves fail too. So you may have reduced your lightning failure rate, but you've increased your shield wire failure rate. Let's say a shield wire could easily, it happens with proper maintenance. It won't, but it's possible to think of a shield wire getting some damage or rust or something and falling on your bus and shorting out your bus and causing problems. So if that shield wire fails once every 50 years, just because you've got a lightning system that won't fail once every 500 years, but you've created a shield wire system that will fail once every 50 years, is it worth it? Right. So again, I'm not saying it's wrong to do. I'm just saying you got to think about it. Lots of things to take into account. You got to take into account. You certainly got to take that into account. All right. Okay. So again, things to think about. Cost, is it worth it to hit that target failure rate if you're really close? Maintenance access. If you put too many obstructions in the way, are you going to be able to access your transformers and equipment that you got to change out? Right. Shield wire failure. Again, okay, great. Your lightning failure rate has gone, to safe levels, but your shield wire failure rate may not be. So that's something to think about. So can you trust your shield wires, I guess? And so I got this photo. You remember this guy? This is the
yeah.
the French. I guess he was a acrobat or whatever, and he climbed up the Twin Towers, and he used like a crossbow or something and shot a shield wire across. he shot a tensioned wire across the Twin Towers.
I don't know if it was
and tightrope walked.
Same guy, but somebody did that recently in Chicago, I think.
Yeah, that's right. They did.
Yeah.
They did. They sure did. Yeah, the same guy who did it over the Grand Canyon or whatever, right? So those guys, they trust the shield wires not to fail, right? maybe they do, but personally, I don't. You know, we can't always say that the shield wires are going to fail or not going to fail. And so the important thing there is when you design your shielding. You know, we talked about, if you remember, we were talking about the combination systems, right? We were talking about how when you have two wires parallel, as long as you're supporting that sphere, it's very easy to protect your whole substation that way.
Right.
And that's a great practical way to do it. Yeah. But a lot of clients, especially in windy areas, are concerned that one shield wire could snap and land on your equipment.
Yeah.
And so they would rather you spend extra money on masts instead of shield wires.
Right.
You know, obviously wires are far cheaper than masts, right? But, you know, if you're in an area or you're putting shield wire over bus, you know, that is a risk itself in the shield wire falling.
Right. I guess a mast is stronger and, you know, less likely in the event of like a tornado or something like that.
Yeah. You know, the mast itself could fall down, but certainly the wire snapping off and falling is far more likely. Right. Yeah. So, you know, and I'll say this: we have a lot of clients in hurricane areas and you know, Florida, because obviously there's a lot of lightning in Florida, and some of our clients will say no shield wires at all. Some of our other clients will say shield wires are okay, just make sure they don't cross bus. That way, if they fall, hopefully they'll fall straight down. You know, they won't always. There's tension and they could snap and move a little bit, but hopefully they'll fall, generally speaking, downward and not land on bus or something like that. And whereas others say, go nuts. You put as many shield wires as you want. We don't have a problem with shield wires falling, and we care more about saving the money. So it's something to consider, something to think about with your client and the environmental factors.
I imagine here again it might depend on how important the substation is too.
That's right.
I mean,
absolutely.
Okay. Yeah,
that's a very good point. You don't want a very important substation to fail because of a shield wire, when you could have just put maybe a couple more masts. Will cost you, you know, maybe $100,000, $200,000 more, but that may be worth it.
Right.
That may be worth it.
Yeah.
Good point. All right, number 6, and we talked about this briefly too, setting too low of a failure rate, especially for a partial study. Remember we talked about if you do a failure rate for one area, or you're doing a failure rate that's too low, and that site may expand. Right? If you have one failure in 100 years for the first half of the substation, and then 10 years from now you expand the substation and double the size, and you use the same one failure every 100 years, you now have, according to this formula, 2 failures every 100 years. Yeah. Right? Or 1 failure every 50 years.
Right.
So you will violate your own area. So you violate your own design criteria, the only limit that you set, one failure every 100 years, whatever it is. So yes, think about, could this substation expand? And every time you expand the substation, anytime you do a major change to the substation, you should look at the whole substation again from a lightning perspective and see what is the failure rate now. Or if you already have a lightning study done for that substation and you have a failure rate, make sure you go back and you can calculate the failure rate of just the new area, but you've got to go back and add it to the failure rate of the old area to get the failure rate of that whole substation. Right.
And then decide if it fits in your design criteria or not.
That's right. That's right. Yeah, see if does it still satisfy the design criteria limit that you made. So just some brief acknowledgments for some of the photos and of course the IEEE standard. And well, that's about it. Any additional questions? Was that
no,
great discussion? Did you feel like you learned a little bit more about lightning?
Learned a lot.
Okay.
Thank you.
Good. Great. Well, thanks for watching. Thanks again for watching. If you'd like more information and also a document that details all the formulas and all the variables, please go to my website at the address below. Take care.